Let's start with the first topic. First topic we have work. So before understanding the definition of work, let's understand the examples. Means from the example we will see in which case work is done on a body and in which case work is not done on a body. So from the previous knowledge, just tell me in which case work is done and in which case work is not done. First example we have a person pushes a wall. As person is applying force on the wall, but in this case displacement of wall is 0, so work is not done here. Next example we have a man is walking on the ground. As man is walking on the ground, force is applied on the ground and the man is moving in the forward direction, so here work is done. Next example we have a man is studying. While studying, although it is a mental work, so mental work is there, but according to physics point of view, physical work is not there, so displacement is 0. So here work done is also 0. Next example we have while eating. While eating also, this is not considered under the work of physics, so here also work is 0. Next example we have while bicycling. Means when we apply the force on the bicycle and the bicycle moves in a forward direction, so in this case force is applied and displacement also occur. So this is the example of work done. So work is done here. Next example we have a person is applying a force on a body and body also move, but here work done is 0. This example is little bit complicated, that also we will do in further next part in special cases, but for the time being here just see a person here, the weight of this arrow is in the downward direction, which is a force, and the displacement occur in this direction. So although force and displacement is there, but angle between them is 90 degree, so that's why this work done is 0. But still this special case we will do in the next part. Next we have a boy is applying a force on this dumbbell, so here force is applied and displacement of body is also occur, so here work is done, but here work is not done. So now let's see the definition of work. So work is said to be done only when force is applied on a body makes the body move. It means that when we apply a force on a body and body displaces, so this is actually the work done according to the physics point of view. Means we are applying the force and the body moves in the direction of force, that is called work done. So now let's derive the formula of work done with some example. So one example we have two boys moving this roller. So as two boys moving a same roller, so they are applying the same force. So when they are applying the same force, so in this case force is same, means this is a boy, this is B boy. So force applied by A boy is equals to force applied by B boy. But the displacement occurred by A boy, means displacement covered by A boy is more than displacement covered by B boy. Now tell me, out of A and B case, in which case this work done is more? So if you see carefully, here displacement is more. It means this boy apply more work done in order to move this ball. Although the force is same, but displacement is more in the first case, in A case. So that's why work done in A case is more than work done in B case. Now if you see the result, means if you conclude that what is the relationship between work done and displacement. So here work is directly proportional to displacement. Here S signifies displacement. Okay. Now carefully see, work done is directly proportional to displacement, means more is the displacement, more is the work done. Now let's see one more example. In next example, both boy covers the same displacement. As both boy covers the same displacement, but force is different. In first case, roller size is bigger, so this boy has to apply more force. So force occurred by A boy, force applied by A boy is greater than force applied by B boy. Displacement in these cases are same. So now tell me, in which case work done is more? as this boy has to apply more force, so in this case, in A case, work done by boy is more. So work done by boy A is greater than work done by boy B. Now let's find the conclusion from this part. So more is the force, more is the work done. So work done and force are again directly proportional to each other. So now from these two formulas, make the formula work done. Work done is directly proportional to displacement, work done is directly proportional to force. So from these two equations, work done is directly proportional to force into displacement. Directly proportional sign we will convert it into equal to sign by adding a constant k. Okay, so now take k value as 1. So now here we got work done as force into displacement. So what is work done? Work done according to the measurement point of view. Measurement means in order to find the value of work done is force product of force into displacement. So now let's see the definition of force work done. So definition of work done, we have the amount of work done by a force is equal to the product of force and displacement of point of application of force in the direction of force. What is the meaning of this? Carefully see, work done formula we have force into displacement of point of application of force in the direction of force. Here for example, I have one block and I am applying a force on the block. So this point where I am applying a force, this point is called point of application. Point of application of force. When I am applying a force on this block, so the block moves in this direction. So the block starts moving in the direction of force. As the block start moving in the direction of force, so that only is a work done. Means force is in this direction and displacement occur in this direction. So product of these two values gives a work done. So definition must, now it's clear that work done, amount of work done is force and displacement occur in the direction of force. This part is very important. Okay, so now let's talk about that work is a scalar quantity. What is the meaning of this? It means that work does not depend upon the direction. What is a scalar quantity? Which only depend upon the magnitude but does not depend upon the direction. It means that if you apply force in this direction and displacement occur in this direction, so you will get some work done, F into S. Now apply the same force in this direction and same displacement occur in this direction, so again you will get work done as F into S. It means that although you are changing the direction, force and displacement value is same. By changing the direction, magnitude of work done will not change. So if magnitude value of work done or any sign will not change, positive negative sign will not change, so it means that work done does not depend upon the direction. When any quantity does not depend upon the direction, that quantity is called a scalar quantity. So that's why work done is a scalar quantity. Okay, now let's see the expression of work when force is applied not in the same direction of displacement. What is the meaning of this? Carefully see. In the previous definition, we have seen that work is done on a body when force is applied on a body and body displaces in the direction of force. But here the body not displaces in the direction of force. Why? Because force is acting in this direction and displacement occur in this direction. It means that force and displacement are not in the same direction. So what is the formula of work done when force and displacement not occur in a same direction? That formula we have to derive. Okay, now let's see how we will calculate the work done when force and displacement is not in the same direction. So in this case, force is applying in this direction and displacement occur in this direction. So force direction is this, displacement direction is this. So now what we will do, carefully listen. We have two choices according to the definition of work done, that is force occur in the direction of displacement. So what we can do, either we can take displacement in the direction of force, or we can take force in the direction of displacement. So in this expression of work done, what we will do, we will take displacement in the direction of force. So if you will see, here we have three direction. If I make a right angle triangle here we have three directions, named it as A, B, C. So here we have AB direction, BC direction and AC direction. AC is the actual displacement covered by the block, but AB is a displacement covered by block in the direction of displacement. Okay, so here if you will carefully see, so here if you will see the block, so this direction is force direction, and displacement covered by the block in the direction of force is this shadow. Okay, so this displacement now we will calculate. So here force is here. Now when we will make a diagram, so this angle is 90 degree. So this is the displacement which occurs in the direction of force. Okay, angle between the force and the displacement is theta. Now what we will do, we need, see, theta, in front of theta we have perpendicular, 90 in front of hypotenuse, and rest is base. Here we will use trigonometric formulas, which is Pandit Badri Prasad Har Har Bole Sona Chandi Tole. This you have done in math, or you will do in math. Now carefully see, here you need what? Here you need base. As x we have to calculate displacement in the direction of force, and hypotenuse work as a displacement. So these two things we need. Okay, so we need base and hypotenuse. Base and hypotenuse covered with this c. C here is cos theta. So in triangle ABC, cos theta is base upon hypotenuse. Cos theta remains same. Base value we have x, and displacement hypotenuse we have displacement. So x value we got by cross multiply as s cos theta. Now carefully see what is work done. Work done formula we have, force and displacement occur in the direction of force. Force and displacement occur in the direction of force. So F is same. So x we got what? X value we have s cos theta. Okay. So here we got a formula, work done formula, as W is equals to Fs cos theta. So this is the formula of work done when force and displacement are at some angle theta. So angle between force and displacement is theta. So work done formula we got Fs cos theta. So here S cos theta represent the component of displacement in the direction of force. This is displacement, but component of displacement in the direction of force is actually a S cos theta. Clear? So here if you will see, W is equals to Fs cos theta. So here work done is force, and S cos theta represent here component of displacement in the direction of force. So this is the first expression and important expression for the numerical point of view when force and displacement not occur in the same direction. Now first thing we have done, we took displacement in the direction of force. Now next case we will see, here what we will do, we will take a force in the direction of displacement. In this case we will make a formula of work done when force we will take in the direction. So how we will take force? So carefully see, this angle is theta. So this is the force which I am taking in the direction of displacement. I am not taking the component of displacement now. I am taking component of force in the direction of displacement. Now this force and this displacement occur in same direction. F dash I am taking here. So here this is a perpendicular 90 degree. So this triangle again ABC. So these angles are vertically opposite. So this angle is also theta. So again, theta, in front of theta we have a perpendicular, 90 in front of we have hypotenuse, and this is base. Okay, now we need v f dash we have to calculate, and f we have act as a hypotenuse. Again, Pandit Badri Prasad har har bole, sona chandi tole. Now carefully see, base we required, hypotenuse we have. Again we will choose which formula? Cos theta. Cos theta is base upon hypotenuse. Base act as a, in this triangle, base act as a f dash, which is the component of force in the direction of displacement, and hypotenuse act as a force. So f dash we got as f cos theta. So what is the formula of work done? Work done formula we have force which is in the direction of displacement into displacement. Here we are taking this displacement, and force we are taking in the direction of displacement. F dash value we have f cos theta into s. So this is the formula we got, similar to the previous formula, that is fs cos theta, or you can also write w as f cos theta s, which is already written. Okay, now carefully see, here work done is component of force in the direction of displacement, and this is a displacement. So if you will see the formula, so here we have w is equals to f cos theta s. So here work done is component of force in the direction of displacement into displacement. So in this two way you will derive a formula when force and displacement occur at some angle. But here good thing is that formula is same. In previous case we got fs cos theta, in this case we got f cos theta. So magnitude wise they are same, and direction wise also same. So here you will get a formula. This expression of work done is very important. Now we will see that work done is a product of magnitude of force, magnitude of displacement, and the cosine. Cosine means cos theta, cosine of angle between the direction of force and displacement. It means if this is a direction of force and this is a displacement, so angle between them is theta. So here work done formula we will got as w is equals to fs cos theta. So this, again I am telling, this formula is very important from numerical point of view. Okay, now we have to see some note points. Note points we have, first is have force is a vector quantity. So force is a vector quantity means it depends upon both magnitude as well as direction. Displacement is also a vector quantity, but the product of force and displacement will give a work done which is a scalar quantity. How it is possible? Multiply of two vector quantities will give you a scalar quantity. Why? Because it is actually a vector dot product. Okay, this is little bit a part of +1, but still I am telling you one thing here, the force and displacement both are vector quantity, but dot product of vector quantity will give you a scalar quantity. So dot product of force and displacement will give you a scalar quantity which is a work done. Okay, so this you have to remember, that force is a vector quantity, displacement is a vector quantity, but work done is a vector product of force and displacement, so it is a scalar quantity. Next we have types of work done, means how many types of work done we have. So basically we have three types of work done. First we have positive work done. What is the meaning of positive work done? Positive work done means when the angle between the force and the displacement is zero, means both force and displacement occurs in the same direction. So that is called positive work done. In positive work done, cosine of angle 0 degree is a 1. 1 means a positive value. Next we have Zero work done. Zero work done means when the angle between the force and the displacement is 90 degree. Okay, so angle between the force and displacement is 90 degree. So cos of 90 degree we have 0, which gives us 0 work done. Last we have a negative work done. Negative work done means when the force and the displacement, okay, force and displacement both occurs in the opposite direction, so angle between them is 180 degree. So cos of 180 degree we have -1, means -1, which gives a negative work done. So we have positive, 0 and negative work done. So one by one we will see the example of these special cases. So first special case we have free fall of a body. So this is example of basically a positive work done. Why? Here force is acting in this direction, gravitational force mg, weight, and displacement occur in this direction only. So force and displacement both occur in same direction, so angle between them is 0 degree. So this is a, here theta is 0, means angle between them is 0. So this is the case of positive work done. Okay, so let's see the example of positive work done. We have in a free fall of body of mass m under the effect of gravity through some height h. So this is a case of positive work done. Next we have a coolie or a boy does a work on a load when he raises it up against the force exerted by a pulley and the displacement are in the upward direction. Now carefully see. For example, either it comes for a boy or for a coolie. Okay. So here the boy apply a force in the upward direction. Okay, and this dumbbell, this weight is having displacement in the upward direction. So both force and displacement occur in the same direction. So boy or a coolie does work done on a load which is against although the gravity, but force and displacement both occur in same direction, angle between them is 0. So as angle is 0, so this work is an example of positive work done. Next we have next special case. This is a basically a rotational case. So here this we have done in the uniform circular motion. If you will remember, there is one centripetal force acting in this direction and displacement occur in this direction. So angle between them is 90 degree. So cos 90 degree we have 0. So this is a special case of 0 work done. So here angle is 90 degree. So if I am taking a circle here, so this is the direction of force and this is the direction of displacement, angle is 90 degree. So this is an example of whole example of 0 work done. Okay. So now for example, a man is standing with a heavy load on his head. Here angle although it is 90, not 90 degree, but still this is a case of 0 work done. Why? Because displacement is not occur here. So in this case displacement is not there. The person is standing at one place although he is applying a force on a body and there is no displacement of body occur. So this is a case of 0 work done. Next case we have, this case we have seen in previous example. A man walks on a horizontal ground while carrying a load on his head or on the side. No work is done against the gravity. Why no work is done against the gravity? Because according to gravity, its weight acting in the downward direction. Weight which is mg act as a force acting in the downward direction and displacement occur in the forward direction. So angle between them is 90 degree. So we know that cos 90 we have 0 and work done formula we have Fs cos 90. Although force is there, although displacement is there, but cos 90 is 0. So magnitude when multiplied with 0 it give a 0 value. So here because displacement of load is normal means 90 to the direction of force of gravity which is vertically downward. So that's why this is an example of 0 work done. Here theta is 90 degree, so work done is 0. So here you will see the condition for a work done by a force to be 0. Under what condition? Under two conditions when force is 0. First condition we have when work done is 0. When there is no displacement, then work done is 0. Second, when the displacement is normal to the direction of force. When the angle between the force and direction is 90 degree, that examples come under the 0 work done. Okay. Next special case we have when a person throw a ball in the upward direction. So in this case displacement occur in the upward direction and weight of this ball is acting in the downward direction. Okay. So angle between force and displacement here is 180 degree and cos of 180 degree will give you -1. It means this is a case of negative work done. So person throw a ball or a boy throw a ball in the upward direction. So due to the gravity, this is a case of negative work done. Let's see one more example of negative work done. When a body moves on a rough surface, as this body displaces in this direction, displacement occur in this direction and force, frictional force applied in this direction. So this force and displacement are occur opposite to each other. So angle between them is 180 degree. Again it is an example of a negative work done. Okay. Now let's see the graph between force versus displacement. So before drawing the graph between force versus displacement, these are basically two cases. So one by one we will see the cases. First case we have when force is variable. Force is variable means what? For example, I am applying a force on this body. Initially force is 0, then force is 1, 2, 3 and increasingly means keep on increasing. Okay, so this is an example of a variable force. Next we have when force is fixed. Force is fixed means for example on a block I am applying a 50 Newton force. Now this displacement occur in the direction of force but 50 Newton is remain constant. So this is an example when force is fixed. Now let's see the example. When force is variable, initially we are applying less force, then force is keep on increasing. So here how graph will form, carefully see. So here I am taking y-axis and x-axis. On y-axis I am taking force and on x-axis I am taking displacement. Here force is variable means initially force is having less value like 0, then displacement keep on increasing and force is also keep on increasing. So this graph is basically like this. Okay, so this is a graph where initially force is 0, displacement is 0. Force's value is increasing, displacement is also increasing. So here we have to see one thing, that in this graph the area under this curve will give you the formula or value of work done. So area under force displacement graph will give you work done. Now if I am talking about this force, I am talking about the force is variable, case when force is variable. So this is a area is 1 over 2 base. Base we have displacement and height we have here force. Okay, so work done when force is variable we have 1 by 2 F into X. So this is a formula of work done when force is variable. And when next we have when force is fixed, when the value of force is fixed. For example, 50 Newton force is applied on a body and 50 Newton is remain constant. So force is fixed and displacement is increasing. So here how we will make a graph. So force is in the y direction, displacement x direction. So here force value is fixed. For example, 15 Newton, force value is fixed and displacement is keep on increasing. So how we will make a work done formula? For example, area we will take here, this area we are taking. Okay, so now how we will make So this is the area. This is basically a rectangle. Rectangle area. What is the formula of area of rectangle? Base into height. Base we have x, height we have x. So work done we will got here F into x or F into S. Now carefully see, we are using the formula work done as Fs. So what is the assumption we are taking in order to use the formula? The assumption is that when force is fixed, means forces keep fixed on a body, it will not changing. Then only we are using work done as F into S. Clear? Next we have work done by force of gravity. For example, this ball is placed on an incline. So what will happen after some time? The ball will move in the downward direction. So here we have some dimensions of this inclined plane. Now carefully see and tell me which force keep this body to move in the downward direction. So which force is acting? So they are talking about force of gravity, means its weight is acting, which is due to the gravity. So weight is acting in the downward direction. Okay, so this ball is moving in this direction. Now tell me, we know we have to calculate the work done. Work done is force into displacement, and displacement occur in the direction of force. We have three dimensions A, B and H. Out of three dimension, which dimension we will take in order to find the work done in this case? So many people think that here we will take A as a displacement because body move in this direction. So this displacement we will take, but A displacement we will not take. Why? Because force is due to gravity. Force is due to gravity means work done, if you will calculate, weight is acting due to gravity in the downward direction, which is a force, and in this direction displacement is h. Okay, in the direction of force displacement is h. So work done we have force is equals to m into g, and displacement in the direction of force we have h. So work done due to gravity on a body we have mgh. This formula you have seen as a potential energy formula, which is derived from the same relation that gravity force is acting on a body, and body moves certain distance, and that distance we are taking it as a vertical height. So if someone asks work done by a force of gravity, then that direct formula we will use as W is equals to mgh. Okay. Next we will see the SI unit of work done. So SI unit of work done, we have to remember this. Work done is equals to force into displacement. Force SI unit is Newton, displacement meter. So this work done of SI unit means work done SI unit is joule. So 1 joule we have 1 Newton into 1 meter. Clear? Next we have, so what is this meaning? It means that when 1 Newton force is applied on a body and body displaces 1 meter. So when 1 Newton force is applied and body displaces 1 meter, that is called a 1 joule work done. Clear? So what is 1 joule work done? When force of 1 Newton displaces a body through a distance of 1 meter, or you can also write displacement of 1 meter, that work done is called 1 joule. Now let's see the CGS unit of work done. CGS unit of work done. Force CGS unit is dyne, displacement CGS unit is centimeter, work done CGS unit is erg. So okay, so 1 erg is 1 dyne into 1 centimeter. So here 1 erg work is defined as when 1 dyne of force is applied on a body and body moves a displacement of 1 centimeter, that is actually a 1 erg work done. So what is the definition? Carefully see. When a force of 1 dyne displaces a body through a distance of 1 centimeter, that is a 1 erg, which is a CGS unit of work done. Now let's see the relationship between joule and erg. So 1 joule we have 1 Newton into 1 meter, and 1 erg we have 1 dyne into 1 centimeter. Now carefully see what is the relationship between Newton and dyne. So in 1 Newton, basically we have 10 raised to power 5 dyne. And if I'm talking about meter and centimeter, this we know 1 meter is 100 centimeter. So now put the values. 1 joule as 1 Newton we will put as 10 raised to power 5 dyne, and 1 meter we will put as 100 centimeter. Okay. Now if you will see the 0, 10 raised to power 5, 6 and 7. 10 raised to power 7 dyne centimeter. Okay. Which is equals to 1 joule. 1 joule you can also pronounce. So 10 raised to power 7 dyne centimeter is equals to erg. Okay, so this is a relationship between the joule and erg, that is 1 joule is 10 raised to power 7 erg, and this is very important relationship. Derivation is also very important. So here we have 1 joule is 10 raised to power 7 erg.